Greetings to everyone at RoboNation. We, Team DTU AUV, are extremely proud to present to you our latest vehicle Lapras, developed for RoboSub 2021 competition. My name is Megha Goyal and I'm a final year student of electrical engineering at Delhi Technological University and I'm the vice captain of the Team DTU AUV.
Hi everyone, my name is Rajat, second year computer engineering student at DTU. I'm part of software department and I'm responsible for vision and control testing of laptops.
Hello, I'm Sandeep, a second year student of computer engineering at DTU. I'm a part of the software department, and my responsibility is to test the vision and controls of the vehicle in gazebo environment.
Hi everyone, I am Siddhant Verma. I am a senior undergraduate student majoring in EC and the head of the acoustics team at DTU AUV.
Hello everyone, my name is Suryansh and I am a first year mechanical engineering student at DTU and I am responsible for simulating various manipulators for Lapras.
Hi everyone, my name is Sujit and I'm a first year electronics and communication engineering student at DTU and I'm a member of the embedded department.
Hi everyone, I'm Chirag. I'm a freshman student at DTU currently pursuing engineering physics and I'm responsible for the sensor optimization of the AUV. Compared to our previous vehicles, the Lapras has a very compact and robust design. We have kept the sensors in the vehicle to the bare minimum, just enough for all the tasks, reducing unnecessary connections and keeping the bot economical. The vehicle has a diverse range of sensors fulfilling the needs as per the various tasks. It has 2 USB webcams for vision and 3 hydrophones for locating the pincher. On the high-level control board, we have a Bosch IMU for stabilization and a bar 30 pressure sensor which gives an accurate depth of the vehicle. The high-level control board also contains the temperature and voltage sensors to measure the respective states. For the gripper mechanism, we have used a current sensor with the servo motor in place of the force sensor.
Now coming to IMU Controls, the biggest optimization we made in Lapras was navigation without a DVL. Using a DVL and an IMU, we had an option of gaining a position estimate. However, since a path or finger is given from every task to the next, we were able to remove a bulky component and make it extremely compact and cost effective. For our orientation needs, we utilize the BMO 750 IMU by Bosch. It integrates a triaxial accelerometer, gyroscope, geomagnetic sensor, and a 32-bit microcontroller running the BSX 3.0 Fusion Lib software. We have experience from previous vehicles and we were able to reliably control roll, pitch, and yaw values as per the competition requirements.
Talking about the camera placement, the front camera of Lapras is placed in such a way that it is in the line with the torpedo and gripper. This helps us to improve our accuracy while performing torpedo shooting and gripping tasks. Similarly, the bottom camera is placed as close as possible to the dropper so that dropper can be easily aligned with the target. Next. It was necessary to estimate distance in buoy, torpedo, and gripping tasks. For that, we relied on triangulation-based distance estimation algorithm instead of using any dedicated sensor. And this algorithm gave us fairly good estimate of distances. Next. For image enhancement, we first thought of working with the see-through algorithm, but see-through algorithm uses RGB de-images and depth camera is very expensive. We decided to work with single image de-aging method, and this method gave us satisfactory results while performing underwater testing on previous year videos. These are the results.
Now let us talk about the acoustic stack. We have used 3 teledyne reson hydrophones which will receive and convert the underwater sound signals into electrical signals. The acoustic stack consists of 2 boards, namely the data acquisition board and the digital signal processor. Here is a block diagram showing the data flow in the sequence of its processing and the components. We have used Maxim's Max evaluation board in which along with the simultaneous sampling ADCs, an integratable programmable amplifier, anti-aliasing filter, and digital filters as well. The data from the data acquisition board is sent to the digital signal processor via the SPI communication protocol. We have used the Texas Instruments Launchx board as our DSP to lay off the strain from our main CPU. This is the bottom view of AUV. The hydrophones have been placed carefully away from the thrusters to reduce the effect of noise in the input signal captured by the hydrophones. The placement was done keeping in mind the dimension of the hydrophones and symmetry.
This is a hypothetical arrangement model designed at scale with the hydrophones kept at a separation proportional to the actual arrangement, which is about 30 centimeters apart as an isosceles triangle. The reason why the arrangement has been kept such is to maximize the value of receiving time difference, which makes the algorithm easier to compute and estimate values. Next slide. The algorithm that we're using is based on two-dimensional time difference of arrival localization. Well, why not 3D? 3D localization, though gives highly accurate finger location estimates, involves matrix multiplications, requires higher computational resources, more number of hydrophones, and is more prone to error. The previous slide. Since locating the finger is error resilient, we thought of using an approximate model of 2D TDOA localization, using 3 hydrophones neglecting the Z-plane delay, which gives a substantially reduced complexity in exchange for some loss in accuracy. In order to compensate for the lost accuracy, we'll be using the camera modules, considering the fact that the finger task includes the presence of visually distinguishable objects present, which will be easier to detect using the cameras. This marginal loss of accuracy for a significantly reduced hardware brought down the cost of the components. Next slide. The TDOA is simple. First, the calculation of time difference of arrival. The source emits a signal at an unknown time which is received by hydrophones at T1 and T2 times. The time difference value of node 0 with respect to node 1 is the difference of those time values. Next slide. Using that time difference value, we plot the locus of the difference of distance for the two nodes, which is a hyperbolic equation. The distance from the nodes is shown in the form of circles, and as these circles of increasing radii intersect, the locus of the difference of distance is formed. Next slide. This slide shows the algorithm shows how the algorithm computes the time difference of arrival for multiple nodes with respect to the one node to form a hyperbolic line of positioning to find the unique solution of the finger. This estimation is done recursively for the AUE to move into the direction of the calculated location. Next slide. For the different values of finger that we tested this model, the estimated 2D values have been pretty accurate, which makes us fairly confident that even if we assume the Z-plane error would be large, the estimated position will be such that the autonomous navigation is performed successfully.
The temperature sensor and voltage sensors have their connections on the higher level control board, and they find their use in the debugging phase of Laplace. The body of the battery hull is made of aluminum, allowing good thermal conduction to the surrounding water, as there is no significant heating in the battery hull. Logic level converter for the pressure sensor is located on the higher level control board such that it is as close as possible to the back of the hull to avoid extra wiring. The gripper. The gripper of Laplace 2.0 has a split body design to make inspection and maintenance work quickly and easily. Modulation is at the heart of the gripper design, making replacement of the damaged parts affordable. The lower part of the gripper case, experiencing on the load, is connected directly to the vehicle's frame, while the detachable cover limits the motion of the gripper mechanism to only necessary rotation. The gripper has a two-finger design, with each finger having a mixed curvilinear and flat inner surfaces, generalizing the shapes of the objects to be gripped. The inner end of each finger has a gear inbuilt and in contact with the other gear at all times. The driving servo motor for the gear is mounted coaxially to one of the fingers. Upon rotation of the servo shaft, the corresponding finger rotates by the same angle, and the finger's gear, which in turn rotates the other finger symmetrically in the counter direction. After prototyping and experimentation, we found a need to upgrade the gripper to be an active gripper.
It is necessary for us to know when the gripper has made successful contact with an object. Else, if the input to the motor is an incorrect angle, the motor will apply a large torque to the load, potentially causing irreparable damage. Hence, the feedback system was initially implemented using a force sensor. The force sensor required waterproofing and a small pad size which could not detect objects of all sizes. So an in-house solution was implemented using an ACS 712 current sensor. The input to the gripper servo motor will be a sweep angle. The current sensor continuously monitors the current drawn by the servo motor. As long as the claws of the gripper do not encounter an object, the current draw will be relatively low. But as soon as the object blocks the claws of the gripper, the current draw will spike because the servo motor will be applying a large torque to try to move the claws to the input position. By studying the current draw, it can be accurately predicted whether the gripper has made successful contact or not. The solution is also cost effective as the force sensor is costly in comparison to current sensor and saves the need of unnecessary waterproofing and cumbersome underwater wiring.
We would like to thank RoboNation for giving us this opportunity to participate in such an extreme competition and learn and interact with individuals in marine robotics industry. We would also like to thank Delhi Technological University and our faculty advisor, Dr. Ajit Kumar, as well as all of our sponsors for their continued support.